Hey everyone, I got a really cool problem for you today. And this is a three-dimensional equilibrium problem, but it's got some real twists and turns to it. We're going to go through the entire problem-solving process with this problem. So here's the problem up here. I got a ball weighing 10 pounds and it's being suspended by 3 ropes or cables. And the position of the mass is at the origin of our system. And then these 3 cables are attached at a ceiling height. And so the actual positions of these cables, or these 3 points of these cables, are here. All right, so there's the information that I've been given in this problem. This is a problem I actually did when I was a sophomore, so that's a lot of years ago. And it's one of my favorite problems because it's got some, again, there's some really interesting twists and turns in here. But as we're looking at this problem, there's a couple of things that I do want to kind of highlight. The first one is it talks about 3 weightless cables. And that's not oftentimes really stressed. We generally assume the cables and stuff in this class are going to be weightless. And we have to do that because if they're not, then the tension in the cable is going to vary from high to low. So think of a chain. If I'm holding a chain straight up and down, the tension at the bottom of the chain is going to be small, but the tension at the top of the chain is going to be large. And so a weightless cable, there's no change in the tension throughout the entire thing. And you could do that actually if you look at the tension in the cable and you've got, just take a piece of the cable here and look at, let's say that the rope is, or the cable or whatever it is, that's left and right. Let's say this is T left and this is T right. If this thing, forget equilibrium, if this thing is accelerating, then T right minus T left is equal to MA. If it's massless though, MA is equal to 0. And so T left and T right are going to be the same, even if it's accelerating. It's a little redundant if it's not accelerating. You know, if you have an acceleration of 0, then T left equals T right, even if there is mass. But when we talk about gravity and normal forces, it becomes a little bit different. All right, so that's a weightless cable. In a similar fashion, when I have massless, weightless pulleys, and I've talked about this in previous videos, if I have a massless, weightless pulley, then there's the change in tension on either side of the pulley is 0. So no matter how they're configured, T1 and T2 here, if this is a massless, massless frictionless pulley, then T1 is equal to T2. Even if it's spinning, it's still going to be T1 and T2 are going to be the same. All right, I don't want to spend a lot of time on that, but I do want to make that point. Okay, so we've read the problem. Hopefully I've been out of the way and enough of it that you can kind of get an idea. So that's the first step, read the problem. Then we want to talk about what are we given or what do we know. And so we get that from the problem. So I've got a ball weighing 10 pounds. So there's some weight, mg, equal to 10 pounds for this ball. And then there are some positions. So I'm going to say the position of the ball is equal to the origin, right? That's just 0, 0, 0. But then there's these 3 points. And so I'm going to call them R sub A. And that's going to be, this will be, actually I'm going to call it R1. So R1 is at 2I plus 5J plus 5K. Whoops. So that's position number 1. And then position number 2 is over here, right? And so I've got, let me just write it over here. So R2 is equal to minus 5I plus 2J plus 5K, and then position number 3 is equal to minus 5I minus 2J plus 5K. All right, and I wouldn't normally do this. Normally I would list them down, but I'm running out of board. Okay, so a couple of things really important on this problem. First, this is a problem from a physics class. And so because it's in a physics class, the z-axis is up. So x comes out of the board, y goes to the right, and the z-axis is up in physics, in my physics classes at any rate. So we're going to take that into account. All right, so there's my given information. The other thing is you'll notice there are no units here. Well, the cool thing is for this particular problem, it doesn't matter. They could be inches, they could be feet, they could be meters, they could be miles. It doesn't matter. And we're going to see why that is in this problem. Okay? So just because we want to kind of keep life nice and uniform, I'm going to call that feet, feet, and feet. But it really doesn't matter what the units are for this, and we'll see as to why that is later. All right, so I've read the problem, step number 1. I've listed my given pieces of information, not as neatly as I would like you to do that, but I've listed all of that, so that's step number 2. All right, step number 3, we want to draw a diagram. So I've done that. The diagram is here, right? So there's my diagram. So you can see X is coming out of the board, Y is to the right, Z is up. Here are the 3 positions. There's R1, R2, and R3. Okay, and then I've shown in this diagram the ball right here at the origin. And then I've drawn the forces on this diagram. So there's tension 1, tension 2, tension 3, and then mg pointing down. So mg is in the minus k hat direction. Again, a little different than what we're used to in engineering, but it's irrelevant, doesn't really matter. You're just going to switch a few of your coordinates around if you want to do it that way. Okay, I noticed that then when I look at the distance from the ball to any of these 3 points, they're all going to have the exact same hypotenuse as far as length goes. And so you've got a 5, a 2, and a 5, a 5, a 2, and a 5, and a 5, a 2, and a 5. So when I go to find the length of these strings or ropes or cables, when I go to find those lengths, they're all going to have a square root of 5 squared plus 2 squared plus 5 squared. It might be -5 or -2, but you're squaring it, so that goes away. And so the square root of 54 is the length of any of these cables. All right. So then I use my principles. So right now, what are the principles involved in this? Well, the principles for this problem are going to be the sum of the forces equals 0, right? And then unit vectors and forces. Let me just say force vectors. Those are the principles that we're going to utilize in this problem. So mostly Newton's second law in static equilibrium, where ma is equal to 0. But the sum of the forces equals 0, then I'm going to use unit vectors and force vectors. So let's do that part first. So tension number 1, here's the unit vector from the origin to point 1. So 2i, 5j, 5k, all divided by the length. And that's the square root of 54. And so you can see if I had feet up here and feet here, that would all go away. If it was meters and meters, it would go away. If it was inches and inches, it would go away. If it was miles and miles, it would go away. The units drop out. And then I multiply this unit vector from the origin to position 1. I multiply that unit vector by the tension. Okay? And then tension 2 from the origin to position 2, so -5, 2, 5, -5i, 2j, 5k, all divided by the square root of 54. And that's tension 2. And then tension 3, -5, -2, 5, so -5i, -2j, 5k, all divided by the square root of 54. So all of these points here, it doesn't really show it in this 3D diagram, but they're all at the same level. They're all at the same level. And so your situation, this is going to look a little weird, but I'm going to do it anyway. Your situation looks something like this. So, unfortunately, I don't have 3 hands, so I'm going to hold this one in my teeth. All right, so you have the 3 cables. Okay, so the 3 cables holding up the mast, and the points are all at the same level. So my mouth level, if you will, they're all at that same the same level. That comes from them all having the same z coordinate of 5. All right, so there's tension 1, tension 2, tension 3, and then mg is minus 10 pounds in the k hat direction, right? Because up and down is z, so that's the k hat direction. And then use the principle, sum of the forces equals 0, so I'm going to do the sum of the x forces. So this plus this plus this, don't forget your T1. There's no x force here. Add these together, and I get 0. Add these together, and I get 0. Add these together, again, T1, T2, T3, and the minus 10 pounds. And all of that's equal to 0. And when I do that, I'm going to get 3 equations. I have 3 unknowns, T1, T2, and T3. So 3 equations, 3 unknowns. And those equations are right here. Okay? So let's just take a look at the first one. 2 over radical 54 minus 5 over radical 54 minus 5 over radical 54. T1, T2, T3 respectively. If I go back, here's T1, 2 over radical 54, T1. Minus 5 over radical 54, T2. Minus 5 over radical 54, T3, right? So that's all of the x forces. 5, 2, negative 2 for the y forces. What do you see? 5, 2, negative 2, T1, T2, T3 respectively, right? And then finally, minus 5, 5, 5, and 5 for all of the y's, and then, or the k's rather, and then don't forget the negative 10. So 5, 5, 5 all over radical 54, T1, T2, T3, and then minus 10 pounds. So this actually doesn't take too much to solve. Notice I got a square root of 54 in every one of the denominators here in the first term. And so this becomes 2t1 minus 5t2 minus 5t3 equals 0. So that one's pretty easy. And then some of the forces in the y, again, the radical 54 are everywhere. So I get 5t1 plus 2t2 minus 2t3. And that's all equal to 0. Okay? And then this last one, I can take the 5s, and the 10 pounds is going to go over here. And so what am I going to left? So the 10 pounds is on the right-hand side, but I can divide the 5 out, so the 10 pounds becomes 2 pounds. And then I'm going to bring a radical 54 in. And so this is going to be T1 plus T2 plus T3 equals 2 radical 54 pounds. Right? And there's my system of 3 equations and 3 unknowns. Right? 3 equations and 3 unknowns. These are my 3 equations, some of the forces in the x, some of the forces in the y, some of the forces in the z. And then my 3 unknowns, T1, T2, and T3. And I can solve this, and if I do that, my solutions will be T1 equal to 10.5 pounds. I'm going to jump to T3. T3 is equal to 15.2 pounds. And then T2 is the interesting one because T2 is negative 11 pounds. And so this goes to my final result, or my final process, step in the problem-solving process. Does the answer make sense? And in this case, the answer to that question is no. And when I was doing this as a sophomore, this drove me nuts. And the instructor was awesome because he would not give in. It's like, okay, if that's not right, what's going on? And that's kind of what I want to talk about. How can I have a negative 11 pounds in this tension, right? Because these are cables, and cables only pull, they don't push. So how can that be? Well, first off, it physically can't be. So there's got to be something in this situation that I'm not quite sure what's going on. And this is where life gets interesting. So what I need to do is, let's go back to the 3D drawing here. I want to look at these 3 points, right? My mass is sitting at the origin of my system. But if I look at these 3 points in the XY plane, right? So let's do that. Let's look at these these 3 points in the xy plane and see what's going on. Granted, this is at z equal to 5, right? But here's x, here's y, here's the mass hanging there. So I've got one at -5, that's way over here, -2, so that's about right there. This one's at -5, +2, so that's about there. And this one's at 2, 5, which is about here. So here's the, so your ropes are doing this, right? Should do those ropes in a different color. The cables. So the cables are doing this. And what are you going to notice here? The mass is not in between these 3 points. The mass is not in between those 3 points. That can't happen. Right? So that would be like holding this mass up. Here's 2 of the pieces of cable, and the third one's in my mouth, which I don't have it now, but I've got to push this out here. I can't do that with a cable. That's got to be like a beam. That's the only way that's going to happen. And a beam can have a negative tension, which is what? That's a compression, right? So this is physically impossible for these 3 points, because if I were to draw a line from these 2 guys and make this a triangle, this mass has to be somewhere inside this triangle. There's no way for equilibrium to exist without this mass not inside that triangle. And so it's a great problem, because one of the solutions, or the solution, gives you a non-reasonable answer. And so then you have to ask yourself, what's going on? Why is that not working? And this is the reason why right here. Right? The mass is not inside that triangle. All right, so I've given you a little bit of a problem-solving process and a good 3D equilibrium problem. So hopefully you kind of caught all that. If you don't, if you have some questions about it, please put them in the comments below. Thank you.